Right, so the next speaker is Chris Herzog, and he'll tell us about the non-local Schwinger model.
Yeah, a non-local Schwinger model. I don't pretend to have the only one. I'm very happy to be here. It's been a while since I've been to Princeton. It's a place that has lots of memories for me, and I really like to thank Igor and Sylvia for inviting me. So the last time I almost came to Princeton was about 2 years ago, and I had a busy teaching schedule at the time, and I had to give my talk remotely. And the talk I'm going to give today is in some sense a sequel of that talk, and is largely due to some questions from the audience that I got at that time from, I think, Zohar and maybe Nadi. So it's work I did originally with Abe Shrestha, who was one of my students. He's since graduated and gone on to other things. And some work I hope it could have appeared this week if I wasn't so busy writing this talk. Work with another graduate student I borrowed from John Weider at Oxford. His name's Ludo Fraser Taliente, talented young man. So this is my picture of the Schwinger model. It's foreshadowing what's to come. I'm imagining I have some electrons that are constrained to move in 1+1 dimensions. But the photons have no such constraint. They're allowed to go out of the plane and interact. Maybe that plane is an extra dimension or an extra 2 dimensions. We'll see how this goes.
So it's a real wire.
It could be a real wire, yeah. Yeah, the question I'd like to ask is the following. I have my electrons on the wire, and I have my sun, which is producing lots of photons in some d-dimensional space. And I couple them together and I ask, what happens? What happens to the system? And we have an answer from 60 years ago, courtesy of Julian Schwinger, when d equals 2, when the sun is sitting in 2 dimensions. And we've had lots of talks about it in this workshop. It's still a very inspirational model for people interested in QCD and other more complicated systems. The photon gets a mass, and the system shares some qualitative features with QCD. There's the answer from my talk 2 years ago, which was a much more formal kind of answer. I'll explain what this means in the slides to come. When d equals 4, for a real wire, 3+1 space-time dimensions, the claim from this talk was that if there's an infrared fixed point in the sense of Wilsonian renormalization group, that fixed point cannot have conformal symmetry and couple the bulk and defect degrees of freedom in some non-trivial way. Now, trivial has a very technical meaning here, which I'll make precise in what comes. And then there's the answer from today, what actually happens? And I'll try to give a slightly, it's not a full answer. I wish I could give a really full, crisp answer, but it's a better answer than I was able to give 2 years ago when I gave this talk before. So this outline of my talk. We'll start by reminding you about what I was saying here 2 years ago, hopefully very quickly. I'll give an even quicker review of the Schwinger model. We've already had half a dozen talks about it, so I hope I can be very brief here. But I want to set notation and then change a few things to show you how the answer comes out when the photons live in d dimensions. And that will be the last part. So why might one care? Well, I've already kind of hinted there may be some foundational kinds of issues about quantum field theory and renormalization group and what's allowed to happen. When you couple these theories, you have maybe some UV description where the photons and the electrons are uncoupled. You couple them together, ask what happens at long distances or low energy. What's typical, what's allowed? There's a real world and motivation here about, you can build these kinds of systems. Not quite this system, but something like a carbon nanotube has a lot of similarities to what this model I'm trying to describe. If you wrap these graphene sheets into these thin wires, the electrons are effectively one-dimensional. They have some linear dispersion relation, and they couple to photons which are out of the plane. And if you set it up right, there can be not too much shielding, so you really do get long-distance Coulomb interactions with these nanotubes. There are connections with QCD via the Schwinger model, and Zohar asked this question last week, or he didn't ask a question, he gave an advertisement for my talk. I don't know quite how he knew what I was going to say, But he was suggesting there might be some connections with flux tubes, maybe close to the deconfinement transition. And so this wire I was drawing on the previous page, it's not really a flux tube. It doesn't have transverse degrees of freedom. It's not allowed to fluctuate. But maybe this is a reasonable way to start thinking about what happens to flux tubes close to deconfinement. If you really want to think about, if there's some massless degrees of freedom in the bulk, how do you couple? What's a toy model for thinking about that kind of process? I don't know. I haven't gotten very far along those lines. And then there's finally my personal reasons for thinking about these things. For many years, I've been thinking about defects in boundary conformal field theories in higher dimensions and what kinds of physics goes on there. Okay, so let's start, since I don't have a lot of time. What did triviality mean? I had something very kind of technical in mind. So the statements in the literature, there's this lore that if I have some theory, a bulk theory that's free, so it could be a free scalar, it could be a free fermion, it could be a free gauge field, and it's interacting with some reduced dimensional, say p-dimensional defect. If the codimension of that defect, if it's not a boundary or an interface, but that codimension is greater than 2, and I insist on conformal symmetry, then there's this lore that this kind of setup is trivial in some sense. And there are demonstrations of this in the literature in certain specific cases. So there's a paper that inspired us to write ours that looks at free scalars in the bulk. And the claim there is that the only exception to triviality for a free scalar in the bulk is a so-called monogamy defect when d is greater than or equal to 4, and a codimension q equals 3 defect when the space-time dimension is greater than or equal to 5. So most of the time, it's not a boundary, it's not these cases, these setups are trivial. And again, I have to say exactly what I mean by trivial, so I beg your patience for a few more minutes. And then our result from 2 years ago is that if you do the same with a Maxwell theory, free gauge theory in the bulk, then surface defects, 1 plus 1 dimensional defects, are trivial in the same way. And I think, having gone through this exercise for Maxwell theory and looked at this paper, it's likely that there's similar statements that can be made about, say, line defects in Maxwell, or free fermions in the bulk, or p-form theories in 2p plus 2 dimensions, or whatever free theory you want to put in the bulk that has conformal symmetry. If you turn this crank, which is a kind of heavy crank to turn, you could write some more papers along these lines. So what did I mean by triviality? So the statement about triviality is that I want to consider a bulk defect correlation function. So O is some operator in the bulk, some local operator in the bulk, and these hatted operators are on the defect. If I can compute that 3-point function, for this object to be well-behaved, non-zero, these OIs, these defect operators, must be effectively generalized free fields. All their correlation functions follow from Wick's theorem. So whatever fields live on the defect that couple to the bulk field, they're all trivial in this sense. They're all generalized free fields. You can compute all their correlation functions from Wick's theorem. That's the claim of this work. Let me give you some intuition for why that might be true, how this argument goes. And I'm burying tons of details, but it goes something like this. So if I assume conformal symmetry, and I assume angular momentum conservation, or I can just, bury that in the rotational symmetry of the conformal group, and I'm applying my free field equations to these bulk fields in the bulk, when I write out this 3-point function, there's 2 terms, 2 conformal partial waves, or conformal blocks, I don't know what you want to call these, some primary that's in the defect operator expansion of the bulk field, and some sum over descendants. There's 2 terms, and each of these terms is singular on its own in a place that has no business being singular. So if I look at these 3 insertions, I've got the bulk operator at x, and the 2 defect operators at y1 and y2, and I draw a sphere around y1 and y2 with these guys at the poles, and I put x anywhere on the surface of that sphere, then this conformal block is singular. And there's no good physical reason for that to be true. And so I'd better get rid of that singularity somehow. And I have only 2 options for doing that. Since there's only 2 of these structures, because of my assumption, I can either play off these 2 constants against each other. I can set c equal to some particular constant times c prime, and that singularity will vanish. Or I can adjust the spectrum of the defect operators. I can adjust these deltas and delta primes, and then the singularity will also go away. These conformal blocks reduce to polynomials, and there's no more singularity. Okay? So unfortunately, what happens typically is that option one is just, it's not available. I'd like my theories to be, reflection positive. There's some unitarity bound on these scaling dimension delta. And so I don't have a delta prime. I have delta, but I don't have delta prime. There's no way to cancel the singularity by balancing these two guys off each other. And so I'm forced to restrict the spectrum. And I turn this heavy crank a little bit more, and I see that I'm led to this statement of triviality, that all the correlation functions of these defect operators follow from Wick's theorem. So that's the intuition. And turning this crank is heavy. This Maxwell field, there are probably smarter ways to do it, but when we wrote this paper, it took several months to work out what the structure of these guys were. Right, so there are exceptions, right? So the boundary case, if I have a boundary, this option one is available. So for example, if I have a free scalar in the bulk, these two operators, these two defect operators that I'm thinking about are basically the boundary value of my scalar and its first normal derivative. And so I'm able to play this game and cancel the singularity using these two guys. Or for the Maxwell theory with a boundary, there's a similar game you can play with currents. Great. But generically, that doesn't work. So for surface defects in Maxwell, most free in the bulk scalar defect theories, this second operator, this shadow operator in the language of conformal field theory, they're below the unitarity bound. You got to restrict the spectrum. This restriction means further that the only defect fields the bulk field can couple to are these generalized free fields, which satisfy Wick's theorem. There's some comments that maybe I can flesh this out a little bit more without getting bogged down in technical details. Again, I was saying that the absence of the shadow operators relies on reflection positivity. So if you were to relax that, relax unitarity, you could probably have a wider variety for normalization group flows. For those with an ADS-CFT history, there are really close connections here to the story of alternate quantization for a massive scalar in the anti-de Sitter space with some radius r. You might remember this well-known relation between the dimension of the dual operator and the mass of the field in the bulk. And there's this opportunity for having, for a given mass, two different operators of dimension delta and d minus delta. Those are precisely the two operators I'm balancing off each other in that expression I wrote a few pages ago. But there's a unitarity bound, which says that these deltas have to be greater than d minus 2 over 2, and so that heavily restricts the range where you can cancel the singularities. And the last comment I made is there's some nice, interesting work. If you relax the free and the bulk assumption, there's recent work by Nat Levine, Miguel Polos, and I think other of his collaborators now as well, where you don't just get two operators in this expression. So if I relax the statement that my bulk is free, then I get a whole infinite sum of operators, and there are other ways to cancel that singularity. But those are still interesting constraints, which these guys explore in these works. Okay, so that's the background. Any questions before I go on? Good. So a review of the Schwinger model. Here I think I get to be really brief in a conference like this. Here's my Schwinger model, a Maxwell term. I've got a coupling between the electrons and the gauge field, and I've got a kinetic term for the electrons, and I've got a mass term, which, because I want to keep things really simple and I'm interested in conformal symmetry, I'm going to cross out. So keep my model as simple as possible. And I'm going to solve it by bosonization, as I think maybe Grisha did on last Friday in New York. So there's this relation between the standard vector current and some derivative of the scalar, and the axial current and slightly different derivative of the scalar, and the mass term and some cosine of the scalar field. And the miracle occurs, right, that I trade what looks like an honest-to-goodness interacting field theory for something with just a quadratic action, something that just couples the gauge field to some derivative of a scalar. And now I can solve it, right? And I'll just remind you how that goes, because I want to make things a little bit more complicated in the last part of the talk. So I start with my quadratic action, the gauge fix. This is a slightly different gauge fixing than people were doing earlier in the talk. I think the favorite gauge fixing in this conference was either setting probably setting A0 to 0. Here I'm using the standard d mu a mu squared term. Do a Fourier transform so I can write everything in momentum space and not worry about taking derivatives, and integrate out whichever field I prefer. So for example, if you integrate out the gauge field, you get a quadratic action for the remaining scalar guy, and it's very clearly a massive scalar, right? So b squared plus g squared over pi. G is a relevant coupling here. G has units of mass, and so the mass here for the Schwinger model is g squared over pi. Great. So I did that really quickly. Any questions about that? Probably not. Okay, good. So now let's go on to the last part of the talk, which is hopefully the most interesting one, the new results. So here was my Schwinger model, and of course I'm going to do something very simple now. Instead of having my kinetic term for the gauge field live in 2 dimensions, I'll have it live in d dimensions. So I'm coupling now my wire to a photon in some higher number of dimensions. And we'll integrate out the transverse bits of the gauge field, and I'll write this slightly formal expression for a kinetic term for the gauge field now, which is back now in 2 dimensions, where I'm dividing by some derivatives. And that function g I can give in momentum space as the following integral, momentum integral. All right. So I went up briefly to d dimensions, I integrated out the transverse bits, and now I'm back now in 2 dimensions with my non-local Schwinger model of the title of the talk. I'm going to bosonize exactly the way I did before. These are the same exact expressions I had before for the mass term, the current, the axial current. I get a very similar looking quadratic action now for my bosonized version of the Schwinger model, where the only difference now is this funny looking kinetic term for the gauge field. And now I'm going to gauge fix and Fourier transform exactly like I did a couple of slides before, right? Just this same thing, but now in my non-local context. And here I am again with a nice quadratic action in momentum space with this funny looking propagator for the photon. Okay, everyone on board?
It looked like
Yeah.
Your expression for G was divergent.
Very good, yes, we're getting there. Not always divergent, but it is in many cases. Right, so the propagator. So the rest of the talk is going to be an analysis essentially of this propagator and trying to extract some physics from it and understand what's going on in this setup.
Chris,
Yeah.
you integrated out the transverse components of the gauge field, but in the remaining 2-dimensional components of the gauge field, they still have variations in the transverse space. What would happen to that?
Yeah, I'm being really fast and loose, and there's some more details in the notes, but I believe those are just free and decouple. There's no, they don't really couple to the charge degrees of freedom on the wire.
But in a sense, there is no this remaining component because there is no field in 2 dimensions, right? So effectively, it's still kind of just interaction between electron after you integrate it transversal.
Yeah, that's right. There's no propagating degrees of freedom for the photon anymore on the wire.
Does it say that? So his question was the gauge field polarized in 0-1 plane still has non-trivial variations in the bulk. So that's not 2-dimensional. That's still d-dimensional. So saying that's 2-dimensional and trivial is a little bit too fast. So A0 and A1 is dependent on the d dimensions. What happened to that was the question, right? And if you say that you integrated it out, that's perfectly fine, but you didn't quite say that.
They don't affect the physics, they don't couple. Those degrees of freedom don't couple to the charge degrees of freedom. Now you might, I guess, take a step back and ask, if I had a real electron with that could spin in any one of 4 dimensions, what exactly do I think? But these are really two-dimensional electrons, so it's.
It's not clear that like if you have a photon propagate from. This is not enough polarization to propagate from zero.
But if I think about a Fourier mode in the higher dimensions, right, that still affects the value of the gauge field where it couples to the electrons.
Yes.
So that,
Yes. No, I mean, I'm being a bit fast and loose. We should talk later. My memory is those just decouple. You can just think about transverse photons that don't still there that don't interact with the electrons. Okay, so let's look at this propagator. So here it is. Here's my integral that I have to do, and as Arkady was pointing out, this is often divergent, particularly in 4 dimensions, which might be the interesting case. I've got, 2 powers of q upstairs, 2 downstairs, and so that would be logarithmically divergent. However, if I focus on the range 2 less than d less than 4, then this is fine, actually. This converges nicely, and even includes a nice physical case of 3 dimensions. And the strategy here is to think about, the full range, 2 less than or equal to d less than or equal to 4, and see if it sheds some light on what's going on in the cases we really care about. So there's a funny little coefficient here that depends on some gamma function, and I plotted it so you can see what it's doing, and indeed it diverges at d equals 4, which is that logarithmic divergence, UV divergence. If you look at d equals 2, well, I have a 1 over p squared there, so I recover the Schwinger model. That's good. I get a mass term. And then funny things happen. You could say, well, I'm just doing dimensional regularization, so maybe I should think about this for general dimension. But really strange things start to happen outside this range 2 less than d less than 4. So for example, this range 4 less than d less than 6, because alpha changes sign, there's actually a tachyon in the denominator here. Or if I go to d less than 2, the spectral density flips sign as well. So that seems like good arguments to maybe ignore those cases, at least for the purposes of today.
May I ask, sorry?
Yeah.
So unless you're in even dimension, it's non-analytic, right? Is there a problem with that, or the origin is?
Non-analytic, yes, absolutely. So I'm going to have a branch cut along the negative real axis. Yeah.
For d larger than 4, the coupling was irrelevant, right?
What's that?
In d larger than 4, the boundary
That's also
coupling
right.
was-
So in d larger than 4, that coupling becomes irrelevant. So
Yeah, so
another reason
you
to
may
maybe
say
not think about it.
you may say that you were not allowed to resound the full series of bubbles in that case.
Yeah. So here's the spectral density. It has fairly nice behavior between 2 and 4. It's nice and positive. This is the negative p squared axis. And you can see this pole, this sort of bump here, which is a memory of the pole in the Schwinger model. But the minute I go below 2, I have some negative spectral density. And indeed, maybe what does Maxwell theory in less than 2 dimensions even mean? So let's focus on this range 2 less than d less than 4. And what I'd like to argue is that in this range, you have a very nice RG flow. So here's my propagator. If I look at large momentum, the p squared term dominates. And if I go back to, say, real space, I can see pretty clearly I'm going to get a 2-point function for a scalar with dimension 0. So this is the UV. I have the decoupled system where I just have a free scalar. If I go to small p, the other term dominates in this range, and I have a scalar of dimension 4 minus d over 2. Okay, so it looks like one way of interpreting this behavior is some kind of RG flow from the free decoupled system in the UV to a scalar, generalized free scalar, if I have to say it, in dimension 4 minus d over 2. So it seems consistent with this earlier triviality result I was arguing for, that if it's going to have an IR fixed point, the stuff it's coupling to on the defect has to be generalized free fields. I find it a little bit odd that d equals 2 is the only case where the IR is gapped. And I was hoping that maybe somebody in the audience armed with generalized symmetries and other such ideas might be able to tell me why d equals 2 is so special. And the other thing that's sort of striking about this is it looks an awful lot like this conformality lost scenario in this old Kaplan's Stepanov paper. So Ofer was talking about this in the context of 3D gauge theories last week, right? The distance of the flow is shrinking as d increases from 2 to 4. It's a flow between a delta equals 0 scalar and a delta equals 1 scalar close to d equals 2, and it becomes a flow from a delta equals 0 scalar to a delta equals 0 scalar close to d equals 4. So maybe that's one way of understanding that divergence, that log divergence we saw in the integral in the previous page. Okay?
For conformality loss, you should have square root behavior of anomalous dimensions, or of dimensions.
Yeah, it's not exactly like that. Yeah,
It's just a free theory. It's more like the other end of conformal window, no, where you lose the symplectic.
Yeah. Oh, I should also point out there's this nice paper by Cuomo and Zhang where they find a very similar looking propagator when they look at a free scalar in 6 dimensions coupled to a nonlinear sigma model on a surface defect. They find almost exactly the same expression here. The only change is that d minus 4 becomes d minus 6. Okay, I'm almost done actually. So finally, the 2D40 case, which is, I guess, the most interesting. So this case was log divergent. So maybe let's, instead of using dimensional regularization to look at it, let's just introduce some UV cutoff. So I'll have a log expression for this G function on the previous page, and my propagator goes over to this form, 1 over p squared 1 plus some logarithm of the momentum. And when I was asked to give this talk, I got kind of excited, or I was kind of excited because I thought that there might be some sort of dimensional transmutation going on where I could use this log to argue there's some very small mass scale that appears sort of along the lines of this BKT transition and so forth. But it doesn't work out that way. The signs are not conspiring in the right way. And there is a pole once you introduce this cutoff, but it's at a very high scale. It's of order the cutoff scale. So introducing this cutoff, it's kind of like giving a size to the defect, right? You had an infinitesimally small wire, and now with this UV cutoff, I have some finite width to it, and that gives me this logarithm. It gives me some pole at order the cutoff scale. And then it scales well below the cutoff. I just have this log running of the propagator. And so it's it's not a conformal field theory. There's a scale dependence to it. It's some sort of scale dependent theory with no clear IR fix point. And this is where my English words fail me. I mean, I have a nice quadratic action. I can solve it, whatever the math is there, but I don't have quite the right words to put around what's happening here still. All right, so some comments about the literature. I'm not the first one to have worked on this nonlinear Schwinger model. There are lots of stuff. If you know the right places to look in the past. Here are some names of people who've touched on this before. Maybe I should spend a little bit more time on the condensed matter literature where this kind of theory goes under the name of Ledinger liquid. In fact, long-range Ledinger liquid. And there are even some papers where they have a 1 over R beta density interaction between fermions, and their beta is basically my d minus 3. But it's a little bit difficult to make these comparisons because the condensed matter literature, even though the fermions have a linear dispersion relation, that slope of that's much smaller than the speed of light. They don't have an explicit photon, it's just a Coulomb interaction. They've got a Fermi momentum, they've got lattice spacing, and so all of their results are explicitly Lorentz breaking. And so it looks very different. It's hard to make direct comparisons. And then finally, there's this nice paper from about 2000 by these fellows where they looked at my d equals 3 and 4 cases. And they argued for the appearance of some kind of fermion mass term. Although looking back now, and also talking to the condensed matter people, they didn't solve it exactly. I don't know why they didn't solve it exactly. They used some improved ladder approximation. And talking to the condensed matter people, apparently this is not something you should do in 1 plus 1 dimensions. Because you will see that there's some sort of phase transition, and then you will know there isn't a phase transition because of Coleman, Merman, Wagner. and then you will know that your approximation that you used is somehow wrong. So the condensed matter people typically don't do this, or if they do it, they're very, very careful. So it's not exactly clear the status of this work at this point, especially given Gabriel Cuomo and Zhang's nice work about Coleman, Merman, Wagner for defects. All right, so some takeaways. I've introduced this non-local Schwinger model that represents the interaction between massless fermions on a wire and a Maxwell field in 2 less than or equal to 3 less than 4 dimensions, or optimistically less than or equal to 4 dimensions. So this case gives some kind of trivial RG flow between free scalars. And the D equals 4 case looks like some kind of runaway RG flow, and it's reminiscent, although not exactly the same, as this conformality lost scenario. There are lots of directions I was sort of thinking about sitting in the audience this week, looking at all the different ways people are using the Schwinger model. You can look at the non-local Schwinger model in this way as well, if you'd like to. I have some results on Wilson and Polyakov loops that I didn't have any time to show you. But there's other things you could do too, like, I don't know, more than one flavor of fermion or fermion masses. You could imagine increasing the temperature and thinking about these deconfining flux strings. You could think about symmetry constraints on IR behavior. I don't know if these things are worthwhile or trivial or how they'll pan out, but it's certainly an exciting place to be this week and thinking about all the different ways I could take this work if I wanted to. Anyway, I think that's it. I'll stop for questions.
So in the cases with more fermions, the other ones just stay completely decoupled like in the Schwinger model, or?
Yeah, so there's a renormalization of mass, or not renormalization, the mass becomes the number of flavors times g squared over pi, and then yeah, you get, at least in abelian bosonization, you'll have nf minus 1 of these free fermions floating around, yeah. Of course, if you add masses now, things get much more interesting, fermion masses.
In this non-local model, you add a theta angle in 2 dimensions that doesn't affect anything, right? For the
TSF lives in higher dimension.
I could add a theta angle on the wire, and as long as I keep the masses off, I think I shouldn't add a theta angle on the wire, because I can always rotate the fermions to get rid of it. But yeah, the minute I turn the masses on, then the theta angle, I think, should play an interesting role.
I'm wondering if what you're seeing is just logarithmic approach to triviality when it is for. But I'm not sure. It feels like it might be.
Yeah, I think there's some more calculations one should do, like, I don't know, scattering a photon off this wire and seeing what happens as the wavelength of the photon gets larger and larger, whether you can actually see the wire in this limit or something. I was trying to sketch that out last night and was convincing myself that it doesn't just go away at long wavelengths, but
What's the difference also in, say, if you take lambda pi for theory, say it approaches in 4D, it also flows logarithmically to a trivial theory. If you take the 2-point function of pi squared, you have a 1 over log. The denominator doesn't go away. So it's very similar to your case. You have,
like with logarithmic approach.
Yeah, the correlation function never becomes really free theory because of this law, but still the flows to the theory, right?
That's what I thought.
There are no other questions. Let's thank Chris again.